Welcome to the deep dive. Today we're pulling back the curtain on one of the most critical architectures in modern AI. Basically, the operating system that turns your questions into smart, contextualized answers.
Exactly. We're talking about the Model Context Protocol, or the MCP working process.
And this isn't just, abstract theory. This is the actual blueprint for how these AI systems function in the real world at scale.
Right. We're going to dissect the entire journey of a user request, from the moment you, the user, hit send, all the way until that perfect answer pops up on your screen.
That's our mission today. We want to give you the shortcut to understanding this whole framework, show you how a request flows from, your app through this central MCP framework, how it grabs memory, gets standardized, and then
Finally hits the massive compute power of the AI model itself to get you a response.
It sounds like this really complex dance between being super structured and also being flexible.
It truly is. Think of the NCT framework as mission control. It doesn't generate the answer itself, but without its coordination, the whole system would just collapse into chaos.
Chaos, like it wouldn't be able to remember who you are.
Yeah, it wouldn't remember the user, it couldn't maintain the session, it wouldn't even know how to speak the right language to the core AI. It'd be useless.
Okay, so let's start at the beginning, the starting line. I send a query, something simple like, what's the weather in San Francisco? That request leaves my phone, the client application, and where does it go first?
It immediately targets the framework, and its first job is just to acknowledge that it got the request and then figure out the workflow.
So it's a router, basically.
It's an immediate routing decision.
Mm.
Does this thing need history? Does it need to call out to an external service?
Mm-hmm.
The MCP framework is that intelligent director prepping the request for its journey before it pushes it anywhere else.
That's a great distinction. So the framework itself is the traffic controller, not the engine. But, okay, before we get to the engine, we have to talk about memory. Because if the system treats every single query like it's the first time it's ever heard from me, the results are, well, they're pretty dumb.
They're useless.
Yeah.
And this brings us to, the necessity of memory and continuity.
So what's the first piece of that?
The first, and you could argue the most important memory component, is the context manager. Its job is to manage the dynamic short-term context of the conversation you're having right now.
The conversational thread.
Precisely.
So if I ask for the weather in San Francisco, and my next question is, okay, what about tomorrow, and should I pack a jacket? The context manager is what connects tomorrow and jacket back to San Francisco.
And there's its entire purpose.
Yeah.
It's managing this, high-frequency temporary data. It captures the last few turns of the conversation and stitches them together so the AI model doesn't have to reread everything from the beginning every single time.
And where does it keep this info?
Our source material points out that this information is pulled from a dedicated context storage, which is often, really high-speed volatile memory. It's designed for super quick reads and writes during a single session.
But wait a minute. If the context manager is just accumulating more and more conversational history, especially if I'm in some long, complex planning session, doesn't that become a massive drain on resources?
That is the perpetual trade-off. Absolutely.
Well, how much context can it realistically hold on to before the cost of processing it all just gets insane?
And that's what defines the boundaries of a good context manager. In real-world systems, context is almost always truncated or compressed in some way. It's a constant battle against latency.
Because if it holds too much.
If it holds on to too much history, every single query takes longer to process, and the cost of the input tokens for the AI model just skyrockets. So they have to be really selective, pulling only what's immediately relevant.
Okay, so the context manager is like your brain's working memory. It handles the immediate conversation. But that doesn't account for my whole history with the app, right? Like, I might have told it last week that I only use Celsius.
Right. Or that your home location is always Seattle. That's where the other critical memory component comes in.
And that would be
That's the parallel pillar, state management.
Ah.
So while the context manager is short-term and dynamic, the conversation itself, state management is all about persistence, the long-term relationship. It's tracking ongoing sessions, user history, your preferences, maybe even your subscription status.
So if I were to make an analogy, the context manager is my short-term, what did you just say? But state management is my long-term memory. It's the persistent user profile stored on a disk somewhere.
That's a perfect analogy. And state management provides that foundation for reliability. If the system knows your preference is Fahrenheit, that state data gets injected into the process, which guarantees the AI doesn't start from a blank slate every single time.
You'd have to reconfigure it constantly otherwise?
Exactly. It would be a terrible user experience.
Okay, so let's recap. The request leaves my phone, it hits the MCP framework, and now it's been enriched with both the immediate conversation from the context manager and my long-term profile from state management. It's this very personalized data packet.
Ready to move forward.
Right. And now we hit what you call the translation layer,
Ah.
because the system still needs to talk to the actual AI brain.
And this is where standardization becomes everything. Because now we have to introduce the protocol handler. We've got
Okay.
all these different components, the framework, maybe some other microservices, and then this massive, often proprietary AI model. They don't all speak the same language internally.
So the protocol handler is the mandatory go-between, the universal translator.
Its primary role is to make sure communication across that entire stack is standardized and, just as important, efficient.
What does that standardization actually look like in practice, though?
It means it's enforcing a very strict data structure. Think of it like a schema. The protocol handler takes that personalized request we just built and formats it perfectly into what the AI model is expecting. Often that's a highly structured JSON or protobuf payload.
But why is that so non-negotiable? Why can't the AI model just, handle a slightly messy input? It's smart, right?
Two big reasons, and they both tie directly to cost and performance.
Yeah.
First, the AI model, especially a big one like the GPT-3 example in our sources, is incredibly expensive to run. You want to save that expensive compute power strictly for thinking, not for cleaning up or trying to interpret poorly formatted data.
Makes sense. Don't waste the genius's time with filing.
Exactly. And second, standardization just dramatically limits the ways things can fail. If the system knows exactly what structure to expect, errors related to data ingestion just plummeted. The protocol handler basically shields the core AI from all the chaotic messiness of user input.
So it's a performance optimizer, an efficiency firewall.
It is exactly that.
Okay, so once that package is perfectly standardized by the protocol handler, it's ready to go. But there's still one more gateway, right? The model interface. How is that different from the protocol handler?
It's a subtle but really crucial difference. The protocol handler standardizes the language for the entire system. The model interface is the specialized bridge built specifically to talk to the AI model itself.
The last mile.
It's the last mile bridge. It handles the specific API calls, the authentication, the transmission protocols, all the nitty-gritty details of communicating with that specific model cluster.
So let's say the AI model gets a big update overnight, a new, faster version comes out. What happens to the rest of the system?
Ideally, that headache is shifted entirely onto the model interface.
Ah, I see.
That component acts as a versioning shield.
Yeah.
If the underlying AI model changes its input parameters or its output structure, the model interface is the only piece of the whole MCP framework that needs to be rewritten or reconfigured.
It isolates the change.
It isolates the complexity of model updates from the context manager, from state management, from the protocol handler. It lets the rest of the system stay stable.
That's fascinating. So the whole system is designed to let the most powerful component, the AI model, evolve rapidly without constantly breaking the entire structure around it.
That's the goal.
Okay, we've navigated the request through all this preparation, and we finally arrive at the main event, the heavy lifting and output generation.
Indeed. This is the AI model. This is the culmination of the whole process. After all that prep, all that context injection and standardization, the request finally hits the machine learning model, whether that's, a specific ML application or a massive language engine like GPT-3.
And when the AI model gets that perfectly packaged query, it doesn't just instantly spit out text. There are some critical prep steps it has to do first, right? Things the protocol handler enabled.
Absolutely. The first thing is that the raw text and context have to be converted into a language the model actually understands. It's a step called tokenization. The text is broken down into these numerical tokens, which are the fundamental units of data the model can process.
So even after all that formatting, the prompt is turned into this long, complex sequence of numbers.
Exactly. And right after that, the system does what we can call internal prompt engineering. The AI model uses all that contextual data we got from the context manager to prioritize and weigh the different parts of the prompt.
To maximize the chance of a good answer.
To maximize the chance of generating a useful, relevant response. It's essentially fine-tuning its own internal attention mechanisms based on the history you gave it.
That's a level of pre-processing that, as a user, you never see. But it's what keeps the answers from being super generic.
It's critical.
So once the input is tokenized and engineered, what are the three main actions the AI model then takes?
First, it processes the input data, which means running all the complex matrix calculations. Second, it performs the analysis or prediction. This is the core intelligence part, whether it's writing text or running a forecast.
And third.
And third, having done that task, it generates a raw response.
And that response doesn't just beam straight back to my phone. It has to go back out the way it came in.
It reverses the entire process.
Hmm.
The raw output is handled by the model interface to make sure the format is clean. Then it's passed back through the protocol handler for system-wide standardization, back to the MCP framework for any final checks, and then finally delivered to the client application to be displayed to you.
Wow. This whole journey from me typing "what's the weather" to the temperature appearing on my screen, it's just a testament to orchestration.
It really is.
It means the success of the system isn't just about the raw power of the AI model. It's about how well all these surrounding components manage memory and standardize the communication.
It's the unseen infrastructure that enables what feels like an intelligent conversation. We've walked through the whole MCP working process, the framework coordinating, the context manager providing dynamic memory, state management adding persistence, and the protocol handler making sure expensive compute is never wasted.
And the ultimate goal is to maintain the illusion of a single, powerful brain having a continuous, intelligent conversation with you.
But that illusion is built by all these highly specialized, separate components, each with a very specific, very strict job.
And that brings us back to that central tension we talked about. The context manager is all about flexibility, speed, handling the messy reality of human conversation.
While the protocol handler is the opposite. It's rigid. It demands standardization and mathematical efficiency to save money and prevent things from breaking.
So here's a final thought for you, our listener, to explore. The model context protocol is defined by this battle between chaos and control. If you had to bet which component is the most likely bottleneck in a production system during a huge traffic spike, the chaotic memory system, the context manager, or the strict necessary translator, the protocol handler, think about resource contention versus format rigidity.